Hello everyone, my name is Myoung-Woo Yoo. I'm a postdoctoral researcher working in Professor Axel Hoffman's group at UIUC in United States. In this presentation, I will talk about my numerical calculation results on domain dynamics in non-collinear antiferromagnets. First, I will introduce non-collinear antiferromagnets. Non-collinear antiferromagnets, such as manganese-310 or manganese-germanium, they have such hexagonal atomic structure and tighter magnetic moment configuration. Because of their complex characteristic atomic structure and magnetic configuration, they can have such interesting topological property. We called it Urbana near the Fermi level in the momentum space. And because of the Urbana, the non-collinear antiferromagnets can interact with the external magnetic field, electric current, and even light, despite their negligibly small net magnetization. As you can see in this anomalous Hall effect measurement and magneto-optical Carr effect measurement, we can clearly see different magnetic states in non-collinear antiferromagnets. It is known that the magnetic state of the non-collinear antiferromagnet is determined by so-called magnetic octupole vector. It is a characteristic vector. It can define the magnetic state in non-collinear antiferromagnet. Because the magnetic octupole vector is determines the electrical signal and optical signal of the non-collinear antiferromagnets, we can think that the magnetic octupole vector is analogous to the magnetic dipole moment in ferromagnetic system. Note that the magnetic octupole vector also has a finite magnetic moment value, but its magnitude is about 1,000 times smaller than magnetic dipole moment in conventional ferromagnetic system. Since the non-collinear antiferromagnets can interact with light, we can observe their micromagnetic state using diverse microscopy techniques, in this case, Mach microscopy technique, and we can easily observe their non-uniform complex magnetic configuration, that is, magnetic domains and magnetic domain walls. Similar to the ferromagnets, the magnetic domain walls in non-collinear antiferromagnet can interact with the external magnetic field or electric current. However, it is very difficult to analyze their dynamics analytically because their shape and dynamics are very complicated. In this case, we can perform numerical calculation based on the atomistic spin model, in which we calculate the dynamics of all the atomistic spin in this system using their equation of motion. However, it is practically difficult to calculate their collective magnetization dynamics in micrometer-sized scale using the atomistic spin model due to the limitation of computing power and memory, because there are too many atoms are involved. So the problem is, how can we solve this issue? Fortunately, we already have an important hint to solve this problem in ferromagnetic system. In ferromagnetic system, we use micromagnetic model, micromagnetic simulation to calculate the collective magnetization dynamics in micrometer scale. In micromagnetic model, we don't have to calculate the dynamics of individual all individual magnetic dipole moments. Instead, we set a finite volume where there are sufficiently large number of magnetic dipoles inside, but the magnetic dipoles are aligned in the same direction, mostly same direction, then we can define a representative magnetization of this volume. Then we can describe the non-uniform magnetic configuration based on this magnetic dipole, this magnetization of the volume. If we use micromagnetic model, we can reduce the amount of calculation drastically, 100 times, 1000 times. Then we can calculate the collective magnetization dynamics in micrometer scale in ferromagnetic system. So in this work, we will develop micromagnetic model for non-collinear antiferromagnets, and I will show you a couple of examples. So to build the micromagnetic model for non-collinear antiferromagnets, we need to consider a magnetic unit cell of the non-collinear antiferromagnet, in this case, manganese 13, which has 6 magnetic dipole moments inside. And we already know the Lagrangian and dissipative function of magnetic dipole moment. So by integration, the Lagrangian and the dissipative function over the certain volume, and by solving the Lagrangian equation, we could obtain the equation of motion of the octupole magnetization. Then we can describe such a non-uniform magnetic configuration in non-collinear system, antiferromagnetic system. If we are interested in 10 by 10 by 10 cubic nanometer antiferromagnet element, we need to calculate more than 40,000 spins, atomistic spins with atomistic spin model, but we need to calculate only one octupole magnetization with this micromagnetic model. So to confirm our micromagnetic model in non-collinear antiferromagnet, we conducted several simulations. In the first simulation, we numerically calculate the dynamics of a single octupole magnetization. In this simulation, the octupole magnetization is initially oriented plus y direction, and we excited its dynamics by applying magnetic field in the x direction, like this. Then we plotted the time evolution of the octupole angle from 90 to about 30 degrees and the total magnetic energy. As you can see here, the magnetic octupole magnetization is initially oriented 90 degrees and it stops around 30 degrees because of the 6-fold symmetry of the manganese 13, and it has another ground state around the 30-degree angle. We additionally conducted the same simulation based on the atomistic spin model. In this case, we need to calculate the dynamics of 6 magnetic dipole moments, and we obtained the very identical results. And these results show that our micromagnetic model is in good agreement with the atomistic spin model. In the next simulation, we calculated the magnetic domain walls. In manganese 13, there are 2 different magnetic domain walls, nail domain wall and block domain wall. It is determined by propagation direction, x direction, z direction, because of their atomic structure. And because of the 6-fold symmetry of the manganese 13, 180-degree domain walls consist of 3 different 60-degree domain walls like that. So in this simulation, first we calculated the profile of one of the 60-degree domain walls from the Néel domain wall and block domain wall using micromagnetic model. And this result is in good agreement with the result calculated from the atomistic spin model. And then we also obtained the differences between Néel domain wall and block domain wall using micromagnetic model and atomistic spin model. For these simulations, it took only 2 minutes using the micromagnetic model, but it took more than 40 hours using atomistic spin model on my computer. These results clearly show that the micromagnetic model well describes the non-uniform magnetic configuration in noncollinear antiferromagnets, and it is much more efficient than atomistic spin model. Finally, I briefly show you the domainer motion calculated by micromagnetic model. Note that we could not conduct this calculation using atomistic spin model because of the lack of computing power. So for this simulation, first we prepared three different 60-degree domain walls from 90 degree to 30 degree, from 30 degree to minus 30 degree, and from minus 30 degree to minus 90 degree. Then we excited their dynamics by applying magnetic field in the y direction, like this. Then we obtained their domainer dynamics. From this calculation, we obtained the time evolution of the domainer position from the first domain wall, second domain wall, and the third domain wall for different excitation magnetic fields. And we successfully obtained the domainer velocity as a function of the field strength for 3 different domainer types. I will summarize my presentation. In this work, we developed the micromagnetic model for noncollinear antiferromagnets, and our micromagnetic model is in good agreement with the atomistic spin model, and the micromagnetic simulation, we show that the micromagnetic model is much more efficient at the micrometer scale in this kind of problem. And our work can be used to investigate complex magnetization configurations and their dynamics in noncollinear antiferromagnets at micrometer scale, for example, 180-degree domainer dynamics or 2-dimensional magnetic structures. This is the end of my presentation, and thank you for your attention.
Thank you very much, Myoung, for your very nice presentation. I
Thank
think
you.
we have time for one small question. Anyone, either by chat or you can unmute yourself. So I think if there are no questions, maybe you can discuss any possible questions on GatherTown.